Hello everyone, so let's see how we will determine the optic sign of an uniaxial mineral. The diagram represented as small a, so it represents actually the optic axis interference figure of an uniaxial minerals, but we have to determine whether the uniaxial mineral is optically positive or it is optically negative. So as this is an optic axis interference figure, so we will observe the melatope at the center of this field of view, right? And you can see a crosshair is there. So these crosshairs are representing the isogyres, right? Isogyres. Okay. These are isogyres. Okay. And look at the melatope, the retardation amount is exactly 0 because optic axis is present along the M, right? Along the melatope. So as you go away from this melatope, you will see that the retardations is increasing gradually, right? So you will definitely observe some isochromes in this way. Okay, they are actually isochrome. Okay, so isochrome contain all the points of equal retardation. Clear? And we already know that E ray and O ray vibrations are present in this field of view. Okay, and the vibration direction of omega ray are tangent to this isochrome, right? So they vibrate tangentially with the isochrome. Okay. Look, so these all are actually the vibration directions of omega ray. Okay, and epsilon ray is vibrating just perpendicular to this. Okay, so these all will be vibration direction of epsilon ray. Okay, clear? Right? So look, suppose all these isochromes, all of these isochromes have some definite value of retardation. Suppose like this line may show you 800 nanometer retardation line, or if you go away from this, it could be like 1200 nanometer retardation line. Okay, 1200 nanometer retardation line. Okay, so the isochrome will definitely have some retardation value, right? And right now what we will do, we will insert a length fast gypsum plate. Gypsum plate. Look, gypsum plate is such plate that can create a retardation of 550 nanometer, right? So as you are inserting this gypsum plate, you can see some color rise and falls in these coordinates, okay, or in these sectors. Clear? Look, suppose this is 1, this sector is 2, this sector is 3, and this sector is 4. Clear? After the insertion of gypsum plate, you may observe that in third and first quadrant, the retardation is increasing. The retardation is decreasing. Suppose in 1 and 3 the retardation decreases. Okay, and at the same time in 2 and 4 the retardation is increasing. So as a result, what you will observe, you will see the change in color. Okay, so as in 1 and 3, color falls, right? So color falls. Okay, suppose color falls from second order red to first order yellow. Or second order green to first order yellow. Okay, clear. So in this sector you will observe the yellow color. In this sector also you will see the first order yellow color. Okay. So what is happening in this part? Look, in this part you can see, just look at the omega and epsilon. So the omega is like this, is not it? Omega is like this and epsilon is like this, right? Okay. At the same time, the vibration directions of this gypsum plate is like, this is fast and this is slow. So look, as a whole, what you are observing, the color falls. So color falls, right? Color falls. So that means retardation decreases. So retardation decreases means the fast ray becomes slow and the slow ray become fast. Okay. If fast ray becomes slower and the slow ray becomes slightly faster, then what will happen? The distance between the fast ray and slow ray will decrease, and as a result retardations will also decrease, right? So how it could happen? Look, this is fast ray. Okay, we know these fast ray and slow ray vibrations of gypsum, right? Gypsum plate. But we don't know the omega and epsilon. So look, if the fast vibration direction falls on slow vibration directions, then only the fast will become slow, right? And if this slow vibration direction become parallel to the fast vibration direction, then it can become faster, right? So the basic thing is, look, this epsilon ray, okay, this epsilon ray is definitely a slow ray. So slow on fast, right? So epsilon ray is here slow ray on fast ray of gypsum plate, right? So as a result, what will happen? Look, this slow ray, as it falls parallel to the fast ray, slow. So this epsilon ray, which is a slow ray, it will become slower, right? And look at the omega ray. Look, the omega ray is actually fast ray. So fast ray falls on, or it vibrates parallel to a slow ray, right? Gypsum. So when fast ray falls parallel to the slow ray of the gypsum plate, so this fast ray will become slower, right? And this slow ray falls on the fast, so it will not be slower, it will be faster. Okay, clear? So as a result, what you are observing, that the retardation is gradually decreasing. Okay, or the retardation will decrease, right? So look, here you can see epsilon ray is slow ray and omega ray is definitely fast ray, right? So look, velocity of the velocity of omega ray is greater than velocity of epsilon ray. Therefore, refractive index of epsilon ray should be greater than refractive index of omega ray, right? So if this thing happens, so look, in case of the indicatrix of uniaxial mineral, for this situation it was optically positive. Okay, clear? So it will be definitely optically positive, right? And now see, suppose in 2 and 3, in 2 and 3, sorry, 2 and 4, suppose color rises. So color rises means what? It means retardation increases. Okay, color rises means the retardation increases. So when retardation increases, when your fast ray become faster, and it will happen when fast vibration directions of the mineral will superimpose on fast vibration direction of the gypsum plate. Okay, and slow ray become slower. This will also will happen if the slow vibration directions of the mineral is superimposed on the slow vibration directions of the accessory plate. Okay, so fast on fast will increase the velocity of the light, and slow on slow will decrease the velocity of the light. So fast will become more faster and slow will become more slower. So the distance between them will definitely increase, and as a result you will see the retardation is gradual, will definitely increase, right? So in case of 2 and 3, suppose color rises, and the color rises from it, suppose it rises from second order green to suppose third order blue. Okay, suppose this happens. So if this happens, so look, these quadrants will be definitely blue in color, right? You can see the blue color of this quadrant, and this color is third order blue. Okay, so in these situations we are observing which things? Look, in this situation omega are vibrating in this direction, right? Omega is vibrating in this direction, and epsilons are vibrating in this direction. Look at this omega and epsilon. In both the 2 and 4 quadrant, you can see orientations of omega and epsilon in this way. And look, the gypsum plate, this is the fast vibration direction of gypsum plate, this is the slow vibration direction of gypsum plate, right? So you have observed that the color rises. So what does it mean? As I told you earlier, that fast on fast makes the fast light more faster. So definitely as the color increases or the retardation increases, so the omega ray should be the faster one. Okay, as a result we are observing fast on fast, right? And this epsilon ray, which is vibrating parallel to slow vibration directions of the gypsum plate, this epsilon must be a slow ray. So omega ray is fast ray, and epsilon ray is slow ray. Okay na? So right now look, v omega, velocity of omega is greater than velocity of epsilon. So that means omega ray is fast ray, epsilon ray is slow ray. So n omega should be less than n epsilon. So again look, the same thing is happening, right? So the same thing, n omega is less than n epsilon. Look. So that means your mineral is uniaxially positive. Okay.